Today's lesson is going to be on double replacement reactions, which is number 4 on our reference tables. And for our double replacement reactions, we're going to use our solubility rules. Now, our solubility rules are going to be really important here because they're going to determine whether or not a reaction actually works. These solubility rules don't become dependent on this reference table, because you will not have this when we get to the AP section. You will have to be able to determine if it is soluble or insoluble from your brain and not from this piece of paper. So don't become dependent on it. Make sure you understand how the solubility rules work. All right, so when we look at our solubility rules, we see that it is soluble. All right, and soluble simply means dissolved in usually water, which is aqueous. All right, so dissolved, I'm going to put dissolved in water, but it could be dissolved in something else. It's just usually dissolved in water. Insoluble is going to obviously be the opposite of that. It is not dissolved in water, usually a solid. All right, and we write a solid with an S when we do our states of matter. Okay, so here we go. Let's look at some solubility rules. Notice we have exceptions, okay? For example, all chlorides, bromides, and iodides are soluble except silver, lead, and mercury 1. Now be careful, that specifically says mercury 1, not mercury 2. So be careful, because some of our exceptions, for example, all fluorides except group 2A, lead 2, and iron 3. So lead 2, iron 3, those are the only types of lead and the only iron that is an exception, all right? This one is really important. All nitrates, acetates, ammonium, and group 1A salts are soluble. This, if you don't learn anything else, I would definitely learn the first two for the soluble and the first two for the insoluble. If you learn nothing else, those are going to be our most important. So we're going to kind of come through this and look at this and work on it. So what I've got for us is some practice. Is it soluble or insoluble? So what I'd like for you to do is I would like for you to pause this video, okay? And I would like for you to determine these 8 substances, if they are soluble or insoluble. And if they are insoluble, we're going to go ahead and make them S for solid. All right. So let's look at calcium nitrate. All right, calcium nitrate. I guess I don't really need to write it out because you guys copied it down when you answered it. Okay, so calcium nitrate, here we go. All nitrates are soluble. There is no exception to that. So number 1, calcium nitrate is going to be soluble, which we're going to write AQ, aqueous. All right, sodium hydroxide. Sodium hydroxide. Sodium is in group 1A. Group 1A is always soluble. But let's take a minute and let's look over here. It tells us all hydroxides are insoluble except group 1A, strontium, barium, and ammonium. And we're going to go ahead and we're going to adjust that as well a little bit later on, okay? So group 1A is always soluble. And hydroxide, that was with the sodium makes it an exception. All right, lithium sulfide. So when we look at our rules here, we see all sulfides except group 1A, which makes sense because group 1A is always soluble. So if you have something in a 1A, it's going to be soluble, my friends. Okay? And number 4, silver chloride. All chlorides are soluble except silver, lead, and mercury 1. So a silver chloride is an exception, so it is going to be a solid insoluble. All right, iron 3 fluoride. So we come over here. All fluorides are soluble. Okay, let me make it better. All fluorides are soluble except iron 3. Iron 3 is part of that exception. So this is going to be a solid. Barium sulfate. So now we need to find our solubility for sulfates. All sulfates are soluble except barium. Barium is an exception, so that is a solid. Ammonium carbonate. Carbonates are insoluble except ammonium. And that should definitely be an exception because ammonium is always what? Soluble. All right, sodium oxide. We know sodium is a group 1A, instantaneously aqueous. If you had looked at your oxides, all oxides are insoluble, but group 1A is the exception to that. So I didn't even need to come over here and look at my oxides. I already knew because sodium is a group 1A. So this is going to be important. We're going to have to use this in order to write our equations. And so if you'll remember, we've started this unit, and within this unit, we've been writing if it's a solid, a liquid, a gas, aqueous as we know it. Well, now we know the solubility rules. So really, we should be able to pretty much anything I throw at you, you should be able to determine if it's a solid, a liquid, a gas, or aqueous based upon all the information we have learned up to this point. So let's look at silver nitrate and sodium chloride. So what we have here is a double replacement reaction, all right? And a double replacement reaction is where we have two compounds as reactants, and they are going to make two compounds as products. We see a swap, all righty? We see a swap. The cations swap with each other, and the anions swap with each other, essentially. All right, so we have the cations swapping and then the anions swapping. So the way I actually do this, and this is going to work for you, is let me erase that so we can make it. I showed you we were swapping. All right, if we take the outside and put them together and the inside and put them together, that is going to give us the correct products. Now remember, the outside is silver and chlorine. Remember, when we write a formula, it is always going to be the cation first and then the anion. We need to look and determine, is this aqueous or not? So our reactants will be aqueous. I'll tell you all that in a double replacement. Okay. Now, when we look at our solubility rules here, we see All chlorides are soluble except silver. So this is going to be a solid. So we've put our outside together. Now we're going to put our inside together. Again, the cation goes first. If you write it in NO3Na, you will lose all points. That is not how we write a formula. We learned how to write formulas in Unit 1. We are now in Unit 6. We've had plenty of practice writing formulas at this point. It is my expectation you are able to do it correctly. The cation goes first. Now, sodium and nitrate. All nitrates and group 1As are always soluble, so this is going to be aqueous. Now, for a double replacement reaction to work, you have to have a solid form. We call this a precipitate. All right, a precipitate is the solid. Okay, so in a solid forms, we call it a precipitate, and we do abbreviate this PPT. All right, so that's our scientific abbreviation for precipitate. If you have two aqueous, then the reaction would not work. We would just write no reaction. Okay, so you have to form a solid in order for a double replacement to work. From there, we can write the net ionic equation. The net ionic equation is an equation that shows us just the players in the reaction. And you'll see I left some space here because I am going to write my net ionic equation. All right, so the net ionic equation, this is going to show us just the players in what makes the reaction work. Okay. And RXN is how we write reaction. This is the abbreviation that we use for reaction. All right, so if you ever see RXN, again, that's reaction. So this shows us just what makes the reaction work. So we have what we call spectator ions. Spectator ions are there, but they are not involved in the actual reaction. And we call them spectator ions because think about it like this. If you go to a football game, all right, maybe there's a football game tonight, and so you go out to cheer on our team, all right, and you've got the football players out there, you are sitting in the stands as a spectator. Now you're cheering on our team, right? And you're cheering them on. They have a good pass. Yay. All right. Good job, guys. You are a spectator. Now, if the team wins the game, do they win because you cheered loud? No. If the team loses the game, do they lose because of you and you sitting up in the stand? No. You did not influence how the team played on the field. You were simply a spectator. You were there during the game, but you did not affect or influence the outcome of the game. The football players were in charge and the ones who influenced the outcome of the game, not you. You are a spectator. So here's how we're going to do a net ionic equation, and let's come back up here to this first equation. Anything that is aqueous, we are going to break it apart into its ions because that's what aqueous means. It's been dissolved in water, so essentially it is an ion in its ion form. So silver plus nitrate. Miss Colson, how did you know silver was a +1 and nitrate was a -1? That's from Unit 1 material. Please go back and review that if you need to. Sodium, chlorine, well, it's an ion, chloride. Solids liquids and gases cannot be broken apart. Solids, liquids, and gases cannot be broken apart. It is just the aqueous. So then we have sodium and we have nitrate. Now, it's important that we start with a balanced equation, and in this case, this equation is already balanced, okay? So we didn't have to go back and balance it further, but before writing a net ionic equation, it is good to go ahead and balance it, all right? Now we need to mark out the spectator ion. So what is not involved? Well, what is the reaction? The reaction is the formation of a precipitate, which is silver chloride, the solid. So it is made up of silver and chlorine. So silver and chlorine right here. What is not involved? Nitrate and sodium. So we are going to mark those out. We are then going to rewrite everything that we have not marked out. So my net ionic equation here is as follows. A silver ion and a chlorine ion are going to form silver chloride. Final answer. All right. So if we look here, this was an example of type A reaction, the formation of a precipitate. We can also do an acid-base neutralization. All right, so let's take a look here at an acid-base neutralization. And that would be something like number 9, ammonium sulfide plus sodium number 9 is not. Number 10, magnesium hydroxide plus sulfuric acid. All right, so here we go. Let's start, and I'll just put it on this paper. Now, this is going to form a salt plus water. All right. Let me give myself more space in case I need to balance it. Okay. So these are both going to be in their aqueous form, all right, for a double replacement. In general, the left side, the reactants are both aqueous, okay? Now, this is going to produce a salt and water. That is going to be our product. So how am I going to form water? From OH and H from the acid. So, again, we're still taking the outside and we're still taking the inside. The H from the acid and the OH from the base makes water. And then what am I left with? I am left with magnesium and I am left with sulfate. So when I swap and drop, I get magnesium sulfate. Now this water is going to be a liquid. And this magnesium sulfate is going to be, if we were to look at our solubility rules, all sulfates are soluble. Magnesium is not an exception. So this is going to be aqueous. All right, so now we need to balance our equation. I have 1 magnesium on each side. I have 4 hydrogens. So if I put a 2 in front and then my oxygens, all right, everything balances at this point. So my next step is I'm going to break all my aqueous apart. I have 2 hydroxides, my friends. Be careful. Plus, I have 2 hydrogen ions. Plus, I have a sulfate ion. Solids, liquids, and gases never get broken apart. This is a liquid, so we write as is, but I can break apart my magnesium sulfate into magnesium and sulfate. Now I'm going to simply mark out what is not involved. Liquid water is what we are producing. That is made from the hydrogen and the hydroxide. So my spectator ions are magnesium and sulfate. So what am I left with here? I am left with 2 hydroxides plus 2 hydrogen ions yield 2 liquid waters. Final answer. Oops. And I didn't draw my box big enough. Final answer.